So guys, let's take a look at chapter 5 together. So guys, question for you. Why did I have you use the 4-quadrant approach to chapter 5? Oh, there's a ton of equations and diagrams, but all of those equations and diagrams were directly linked to concepts. And so guys, the reason that I chose that structure is because I would propose to you that it is a very fitting way to bring that information together, because each chunk of this unit was a concept supported with diagrams trying to make the abstract a little more concrete. But then those, whether they're abstract or concrete concepts, were then described mathematically. And so guys, I bring this up because the reason that I'm giving you, and you're going to see for the entire fall and the early winter, I'm going to be introducing you to different ways to summarize these chapters. Then after Christmas, it is going to be up to you. You will pick the summary strategy that you believe is most appropriate given the material. But guys, again, I would suggest that this was a great way to do this chapter given the content of the chapter. So guys, with that said, what I'd like to do is I'd like to page through chapter 5 with you quickly and give you an overview of what we're up to. So guys, what we're going to do today is we're going to do a whole bunch of, and I'll just be frank with you, terms and definitions. You guys okay? So as we're going over these terms and definitions, guys, there's just no way around it. We need to create a common vocabulary. So we're going to talk about energy. We're going to talk about kinetic and potential energy. We're going to talk about units of energy, joules and calories. We're going to talk about internal energy. We're going to talk about work and heat. We're going to talk about system and surroundings. We're going to talk about closed systems. So guys, this is going to be a whole lot of terms and not concepts. It's going to be a whole lot of terms and definitions. Now guys, along the way, what we're trying to do is not just teach you these terms and definitions, but enough of you have taken or are taking physics. And here's what you're going to find out. And for me, this was very painful in college because I've got a bachelor's degree in chemistry and a minor in physics. And guys, physicists and chemists come at this material, and I mean this literally, from different directions. In the mind of a physicist, you are an outside observer watching things take place. In the mind of a chemist, you are inside the system watching things take place. And why does that matter? All the signs change. So guys, if you've taken physics, this could be a little disorienting at first, unless you were clueless in physics, and then it's not going to matter. But, I know. But if you were tuned in enough in physics to understand that you have place, as a scientist, you have place. Guys, your place is different in chemistry. And so guys, what we're going to do is we're going to go through all of this. We're going to create this common language. And then guys, to end all of this, we're going to play with this block of brass. And it's really interesting how just intricate and fascinating just taking a block of brass and moving it around can be. And that's how we're going to end the day. And you are going to find that it becomes a very kind of compelling and yet rapid fire review of everything that you should understand. So, guys, with that said, today it's all about thermochemistry. Thermo meaning heat or energy, and then chemistry, of course, being this class. So guys, as we get into thermochemistry, the first thing that we should do is define it. Guys, understand that some of you may someday choose to be a thermochemical chemist. It's not a bad way to make a living. But guys, thermochemistry at its very most fundamental is the study of energy changes as they affect chemical reactions. Now, as we then talk about this idea of energy, guys, we need to define the term energy. And let me just tell you this right now. Probably 5 or 6 of the concepts that we're going to talk about in this class during this unit have somewhere between 3 and an infinite number of definitions depending upon the context. When we talk about the first law of thermo, maybe you learned it in physics. Understand, guys, when I teach it to you, I'm going to teach it to you the way you need to know it in here. When we talk about the second law of thermo, it's how you need to know it in here. So guys, when we talk about energy, we're going to talk about it the way you need to know it in here. But understand, if you Google energy and look at the Wikipedia page, the definition of energy is about 3 pages long. I'm going to give you what you need to know. So guys, let's talk about it because we defined this last year. Guys, what did we, and I'm curious to know if you remember, how did we define energy last year? Do you remember? It's not heat. We talked about it, actually, interestingly, we talked about it in September. I'm about to teach it to my general chem kids next time. And if you remember, we talked about tearing a piece of paper, and that was a physical change, and then lighting paper was a chemical change, and it was at that moment that we introduced energy, and we said that energy, do you remember now? No, is the ability to make a change, okay? So guys, if you want to change something, that requires energy. This is the piece of that we didn't talk about that we will talk about this year. This is going to be our working definition for energy. Guys, energy is the ability to do work or transfer heat. So, does that definition contradict what you learned last year? No. How is it in keeping with what you learned last year? What is energy from last year? The ability to make a change. What is it now? The ability to do work or transfer heat. But guys, what do you have to do in order to change something? When I rip paper, guess what I'm doing? Work. And when I light this on fire, I'm transferring heat. So guys, what this is doing is actually talking about the 2 avenues through which we can make change. So maybe a complete definition would be energy is the ability to make a change which is done by doing work or transferring heat. And guys, that's the way things in our universe change, is by doing work or transferring heat. So now, of course, what we need to do is we need to talk about what types of energy are there, and then we're going to talk about work and heat. So guys, let's do types of energy first. I think you know this. What are the 2 types of energy? Kinetic and potential. What's kinetic energy? Energy of motion. So guys, kinetic energy is energy that is moving. And you do need to be able to quantify kinetic energy. Do any of you happen to know the equation for kinetic energy? There's an m and a squared and a... So kinetic energy is equal to 1/2 the mass of a substance times its velocity squared. Now guys, this is going to become important later, so let's talk about it now. Let's talk units. What are our units here? Energy is measured in joules. But in order for this math to work, your masses have got to be in kilograms and your velocities have got to be in meters per second, the quantity squared. So guys, in order for this to solve out to joules, your masses have got to be in kilograms and your velocity has got to be in meters per second. So guys, functionally then, how much is a joule of energy? Ready? A joule of energy is the amount of energy that a 2 kilogram mass possesses traveling at 1 meter per second. So what on earth does that mean? Well, 2 kilograms of water is 2 liters, right? So imagine a 2-liter bottle full of water, and imagine that 2-liter bottle is moving at 1 meter per second. That 2-liter bottle of water then has 1 joule of energy. Does that make sense? A little bit of a frame of reference for that. So remember kilograms and meters per second. You good? Okay. So guys, we'll talk more about kinetic energy later. Let's now talk about the other type of energy, which of course is potential energy. So guys, if kinetic energy is the energy of motion, what is potential energy? Well, okay, but what is it? It's stored energy. So guys, potential energy is stored energy. But now you're going, wait a minute, that's not what that says on the board. The board says that potential energy is the energy of position. You guys ready for a really interesting deep thought? How do you store energy? Position. So guys, for those of you that have a background in physics, you may remember this game. Bradley, be careful. You may remember this game that you've got a block, and we understand that there's this thing called gravitational potential energy, and when this block is on the ground, it has no gravitational potential energy. But when I do work on the block by lifting it, now this block is storing energy. It did not have potential energy sitting on, in the eyes of a physicist, it did not have potential energy sitting on the floor because it couldn't fall. But now that I lift this block, and probably this is ringing true with your understanding of potential energy, this block now has potential energy. There's energy stored in the block, and all I've got to do is release it, and that energy can then be converted into kinetic energy, and eventually if I were to drop it on my toe, I could impart that energy to my toe and cry like a child. So guys, the idea here is that this would, do you have that much of a background in potential energy to understand that this is energy stored in the block by gravity? But why is it, how is it that gravity is actually a vehicle through which we can store energy? And the answer is position. Potential energy, guys, is always stored relative to force and position. And when we're talking about gravitational potential energy, we're talking about the force of gravity and position relative to ground. Does that make sense? So we can store energy that way relative to position and ground. But that's physics. So now let's talk about chemistry. So guys, when we talk about chemical potential energy, guys, where is chemical potential energy stored? In bonds. So how does that idea map onto this idea of it being positional? Let's go back here. Guys, you ready? Gravitational potential energy, it's easier to see. So let's think about it. Why does this block right now have potential energy? What are the two things that are required? Force, what's the force? Gravity. And then what else is required? Position. So it's position relative to a force. But now as we think about chemistry, we now understand that chemical potential energy is stored in bonds. Is that okay? So where's the force in a bond? What causes the force what causes the force relative to the block? Gravity. Why do things with mass have gravity? We're not exactly sure, but the Higgs boson may explain it. But guys, where's the force in bonds? Yeah. Good. Positives and negatives. See, guys, and if you want to, here, let's catch up. So we understand the potential energy is energy stored relative to attraction. And so, guys, with gravitational potential energy, it depends upon mass, position, and the pull of gravity. But now, guys, try this one. This is what we're talking about now, and we're going to draw pictures. This is what is called electrostatic potential energy. And you're exactly on it. It's the attraction between charges. So guys, let's think about an ionic bond. We've got positive, we've got negative, we've got positive, we've got negative, we've got negative, we've got positive, and so on and so forth. And we draw ourselves a little crystal lattice. And guys, how is it that we can then store energy in ionic bonds? Well, we've got all the things that we need. We've got attraction, we've got position relative to that attraction, and consequently energy can be stored in ionic bonds. Now, what about covalent bonds? Let's take the simplest example, which is diatomic hydrogen. Okay, so this is a salt. This is ionic. But what about covalent? Well, guys, let's talk about H2. What is a hydrogen atom? Well, proton and an electron. So here we have a proton, and here we've got its electron. And we can draw a circle around it so it sort of looks like the nucleus. Now, guys, I'm going to switch colors, and let's make this H2. So here I've got another proton, and in order for these two hydrogen atoms to bond together, what do these two electrons have to do? Pair up and share, right? So now we've got a shared pair or a bonding pair of electrons. So guys, what is the charge of this yellow? Oh, that's a really horrible color. What's the charge of that yellow region? Negative. What's the charge of the nuclei? Positive. Now we've got attraction. Now we've got position. Now we've got potential energy. So guys, this is fascinating. The only way to store energy in our universe is position relative to attraction. It's how batteries work. It's how gasoline works. It's how anything. Guys, anything that you can think of that is a way of storing energy always comes back to position and attraction. It's a pretty cool concept if you really dig into it. So, you guys okay with the idea? You're good? Okay, so here's what we then know in summary. So as you suggested, with chemical bonds, we've got the attraction between charged particles. In covalent bonds, it's protons and electrons. In ionic bonds, which are salt, it's the ions. And then, guys, it can actually also be in polar molecules. Water attracted to water molecules to form a liquid. Anytime we've got attraction and we've got position, we've got stored energy. You okay? Did you guys learn that in physics? Probably. Right, you didn't go over the chemical part. So why do we talk about the gravitational part? Because it's easier to visualize. But guys, please don't walk out of this conversation thinking that the attraction between protons and electrons is gravity. Some of you are chuckling, some of you are going, really? Yeah, so guys, understand, do you guys understand that there's only 4 forces in the universe? You're getting this for free. Guys, there's only 4 forces in the universe, and they're all attractive forces. There's gravity, electromagnetism, and then the strong and weak nuclear force. You remember the strong nuclear force that holds the protons and neutrons together in the nucleus. When it ruptures, we end up with nuclear bombs. And then there's the weak nuclear force, which actually holds the subatomic particles together. But guys, that's it. Our universe has got 4 forces. That's all there is. Although they're thinking there may be anti-gravity. We haven't quite figured it out yet. But the 4 forces that we can actually identify are all attractive in nature. There may be offsetting repulsive forces, but we're not sure. So, yeah.
Yeah, what about when you heat something up?
What about?
Really change the position, but energy is not as.
Say that again.
When you heat something up, position doesn't change, but energy goes up.
Well, okay. So, yeah, So hold on. So guys, I know I got a little, I forgot, I can't do that. I know we got a little distracted talking about fundamental forces and anti-gravity. That's not part of the curriculum. Your question is. So guys, Matt is saying when you heat something up, how is that changing energy? So let's answer the question. Because Matt said when you heat something up, the position doesn't change. How are you adding energy? The answer is two parts. One, don't forget kinetic energy. When you add energy to something, it's not just potential energy. It can also be kinetic. And that's really what happens when you heat something up. They vibrate, they vibrate faster. You're increasing the velocity of their movement. But you also can be increasing their potential energy because when things heat, they expand a little bit. So you're also maybe increasing their potential energy a little. Yeah, is that okay? Okay. So guys, we understand these two types of energy. Now let's talk about how we measure energy. And our unit for energy is what is called the joule. Now guys, you already understand this, or at least you've been exposed to it. The joule is the amount of energy that a 2 kilogram mass possesses traveling at 1 meter per second. Here's the problem. That is a very, very small amount of energy. So traditionally, instead of joules, we will use kilojoules, which are thousands of joules. Now, here's the thing. We don't use joules traditionally in the US. What are our units of energy that we talk about here traditionally, especially not in science classes? The calorie. So guys, calories are another unit of energy. Interestingly, they're also metric. I've always wondered why our food doesn't give the energy content in the British units, which are actually British thermal units, BTUs. For some reason, here in the US, we use the calorie even though we don't use anything else metric, which I've always found interesting. But guys, this is the definition of a calorie. It is the amount of energy needed to raise 1 gram of water's temperature 1 degree Celsius. So guys, how does it convert? Well, just to give you a frame of reference, 1 calorie is equal to 4.18 joules. So that sort of gives you a sense of how small a joule is, because it takes 4 joules to equal 1 calorie. But then guys, you've got to understand that this calorie is not the calorie that's on your food. Do you guys understand that? That when you get a Snickers bar and this Snickers bar tells you, oh, don't do that. Guys, this Snickers bar says 250 calories. These calories are not these calories. Dietary calories are actually kilocalories. So when you eat a Snickers bar that has 250 calories in it, it's actually 250,000 of the chemistry calories that we're talking about to raise 1 gram of water's temperature 1 degree Celsius. And you'll notice if you look on your food, the way to know the difference is that the calories on our food are capitalized. They're understood to be kilocalories. Now here's the thing that's interesting. You go overseas and you buy snack foods, and if you look on the back at the nutritional stuff, guess what the units are for the energy in the food? Kilojoules. Yeah. Yeah. Actually, for some reason I thought it might have been your brother, but I don't think it was. Somebody who, oh, now I feel horrible. It wasn't, no, somebody brought this to me last year. I know who it was. It was, oh, poop. It doesn't matter. But now I feel bad. I can't think of it. Anyway, but guys, really, in countries where we use the metric system, not here, they actually measure food values for energy in kilojoules. So now, guys, let's talk about this. The amount of energy that's stored in those M&Ms, is that potential or kinetic? It's potential energy. And where is it stored? in the bonds inside the sugars and the fats and all of the other molecules inside there that our body can break down and then turn into energy and byproducts. Now, guys, we're not going to talk about it. We'll talk more in a little bit, but well, a couple days. But do you get the idea, Matt or Mark or some? You're okay? Okay. All right. So now, guys, we need to shift gears a little bit. We now understand these things. We understand that energy is the ability to make a change. How do we make a change? Work or heat. We now understand that there's two types of energy. Kinetic, which is in motion, potential, which is stored. And now we understand that to store energy, it requires attraction and position. In addition to that, we now understand that we store or that we measure energy in units joules, which is what we'll use in here, or kilojoules, because joules are itty bitty. And then we'll also, we understand that a calorie is another unit of energy, but it's not the one we're going to use. Okay, so now, guys, we're ready to pick up a couple new thoughts. And the thought is the frame of reference that we use when we talk about energy changes. And guys, these are the terms that you need to understand relative to this concept. So guys, anytime we are studying a chemical reaction and we are thinking about it thermochemically, the very first thing that we have to do is define our system. Now, guys, who gets to define the system? You. So what are the rules for defining the system? And guys, the rule is simply this. Make it as simple as you possibly can. You want to hone in on that system so that it encompasses exactly what it needs to and nothing more. Because anything else that you include in your system is going to make the math a lot harder. So what then is the system? And guys, the system is simply the portion of the universe that you are singling out to study. And guys, here's the thing that's nice. Once you've figured out your system, everything else becomes the surroundings. Now, as we talk about systems, the portion of the universe that we're studying, we are going to create a common understanding. And guys, the understanding is this. Our systems will always be what we call closed systems. Then, of course, the question becomes closed to what? And guys, the answer is this. In a closed system, energy can get in and out, but matter can't. And guys, if matter can never get in or out, that means that we will always obey the law of conservation of mass. Now, are closed systems fictitious systems like ideal gases? You know, ideal gases we talk about because they're kind of convenient, but they don't really exist. What about closed systems? Oh no, they really exist. It's really not hard at all to create a container that lets energy in and out but keeps all the stuff in, right? I mean, you've experienced that. A can of Coke, you put it in the fridge, there's Coke inside the can and it's cold. You set that out on the counter, the Coke doesn't go away, but energy gets in and it warms up. So guys, most systems that you're accustomed to, well, not most, but it's very common to actually, this is not fictitious. Closed systems actually exist. Is that okay? Okay, now the question becomes this. How on earth does this happen? How does energy get into or out of the closed system? And guys, you actually already know the answer to this because it was like the second thing that you wrote down, but now we need to bring this full circle. So here's what we now understand. When we study thermochemical systems, we will identify the system and everything else becomes the surroundings. Then our understanding will be that our system will be a closed system. What does that mean? It means energy can get in and out, but matter can't. So now the last thing we need to talk about is how does energy get in and out of a system? And guys, the answer is only two things: work and heat. That's how to get energy in and out of a system, and that's how we're going to wrap up today. So guys, we are now going to talk about how does energy get in and out of a system. And guys, the answer is quite simply work and heat. But this brings us to a term that we need to share, and the term is internal energy. You know what? I'm going to change that word. Let's make this come all the way full circle to this. Rather than substance, let's go system. And then it really ties back. So guys, the idea is this: there are only two ways to affect the internal energy of the system. And I'm realizing that as I put that on the board, I'm thinking something that maybe you're not. So let's talk. So guys, when we talk about the internal energy of a system, we're talking about the energy inside of a system. Now, how many different kinds of energy are there? And the answer is not work and heat. How many different kinds of energies are there? Two. They are kinetic and potential. So guys, you may want to write this down around this. So we've got energy, kinetic, and we've got energy, potential. And if you add up the kinetic energy of a system and the potential energy of a system, that adds up to what we call the internal energy of the system. Now, from there, there's only two ways to change the internal energy of a system, and that is work and heat. Work is abbreviated W, heat is abbreviated Q. I don't know why. So guys, now all we've got to do is we've got to define work and heat, and we're going to wrap up the day. This was going to be a lot of terminology stuff. So guys, let's talk work first. Ready? So guys, the definition of work is energy used to move an object against a force. So work is the energy that's used to cause an object to move against a force. So then we need to talk about what is a force. Well, guys, a force is any sort of push and pull. The broom. So guys, interestingly, if you have a summer job or a job during school, your employer is actually paying you to do work, right? That's why they call a summer job work. I have to go to work because they want you to work. They're paying for you to do work. Okay, so if your job is to sweep, and if you spend the majority of your time doing this, leaning on your broom, are you doing work? Why are you not doing work? You're not moving. See, guys, in order to do work, you've got to have two things. You've got to have movement. If the work that you're looking at are system, if the work that we're looking at is to move this broom, if this broom ain't moving, you ain't doing work. So if you're driving up I-15 and you see a bunch of these guys in yellow jackets leaning on their shovels, and you're saying to yourself, man, look at those guys at work, you're wrong. Because they're not working. Because they are not moving. So guys, you've got to understand that in order for work to be happening, there's got to be movement. But what else does there have to be? Resistance to that movement. Now guys, typically that's always the case because we've got friction, we've got inertia, we've got all of these resistant forces. What you're going to find out though, guys, in chemistry, we're going to get rid of the resistant forces. We on Wednesday are going to get rid of work. And we're going to get rid of work not by getting rid of movement. We're going to get rid of work by getting rid of resistance. And we'll talk more about that on Wednesday. That's what enthalpy is all about, if you remember reading that. I'm guessing that that went in the question section of your things where you're going, what the heck is enthalpy? Guys, that's where we're headed with this, is we are going to make work impossible. But we're going to make work impossible not by getting rid of motion, but by getting rid of resistance. Okay? So that's work. The other, and I guess I think there may be one question in homework where you need the equation. Or maybe it's just nice to see the equation because it actually represents the definition. Work is force over a distance, and that force is overcoming the opposing force. So now, guys, let's talk about heat. You ready for this? Look this up if you like. Please don't write this down. If you look up the technical definition of heat, the technical definition of heat is any exchange of energy that can't be attributed to work. Guys, that is not the definition that we are going to use. We are going to talk specifically about the exchange of energy that is due to temperature differences. And guys, what is temperature actually a measure of? The speed the particles are moving. And so when fast things and slow things bump into each other, energy is transferred from the fast thing to the slow thing, cooling down the hot fast thing and warming up the slow cold thing. And so in our tight definition that we need for this class, we are going to say that heat is the exchange of energy, if I can say this to you, across a temperature gradient from hot to cold. Heat never travels from cold to hot. It always travels from hot to cold. Does that make sense? Okay. All right. So guys, here's the deal. Right now, there's a very real chance that your head is just swimming. Let's review. So we started the day by talking about energy. We said that energy is the ability to change something through work or heat. You'll notice that's also how we ended the day. Then from there, guys, after we talked about what energy was, we talked about the two types of energy that exist. Most of you were comfortable with kinetic energy, which is the energy of motion. And now you maybe learned something about potential energy. Most of you knew that potential energy was stored energy, but now you understand to store energy, it requires attraction and position. And so we talked about that first relative to gravitational potential energy, but then we related it to chemical potential energy, where we've got the attraction, as you pointed out, between charged particles, and those positions of the atoms about those attractive forces, electrostatic forces, allow energy to be stored. Then we quantified energy. We said we quantify it using the Joule, which is a very small amount of energy, and we defined it 2 kilograms, 1 meter per second, but we know it's small, so a lot of times we use the kilojoule, and then we related it to the calorie, that more familiar unit, and we said that approximately 4 joules is a calorie, realizing that that's not a dietary calorie, because dietary calories are kilo, or thousands of those little calories, of which there's 4 joules to 1 calorie. Then, guys, we started to talk about system and surroundings, and we said that the system is up to us. We want it as tight as we can get it, but the system is the part of the universe that we are studying, and then the surroundings is everything else. Then we said that our systems will be closed systems, which means that energy can get in and out, but matter cannot. And now we've just finished the conversation by talking about how energy does get in and out of a system, and it does that through the avenue of work, which requires force and movement, opposing force and movement, and then heat, which is simply the transfer of energy from a hot to a cold object. How'd we do? Pretty good? Yeah. But of course, you guys picked all this up just from reading chapter 5, right? Okay. So guys, you ready? We have about 10 minutes left. Stop taking notes. Go ahead, Matt. Depends on the result. Okay, guys, you ready? Put your notes away. Not put them away. Tuck them to the side and watch. So guys, now what we're going to do is we are going to fiddle around with this brass block. You understand that we're not packing up. This is the most important part of the day. So guys, I am going to bombard you with questions. You have absolutely no idea the physics of this little block. It's fascinating. So you ready? Here we go. That block is now my system. Okay? So if that block is the system, what does that make me? The surroundings, right? What does that make you? What does that make the table and everything else? The surroundings. Now, in order for you to be able to see, we're gonna change things up a little bit. In order to think about potential energy, what does potential energy require? Position and attraction. But guys, with gravitational potential energy, it also requires ground. Right? Because to get that kinetic or that potential energy out as kinetic energy, it's going to fall and you can't see the floor. So we're going to pretend that my countertop is ground zero, that we can't fall beneath this. And so if this countertop then becomes our new understanding of the 0 point ground, how much potential energy does that block have right now? 0, right? So, is there a gravitational force acting upon it? Yes. Why does it have no potential energy? Due to its position, right? We're just going to flow. I'm not going to do questions. So guys, it has no potential energy due to its position. Does that make sense? Now, does it have kinetic energy? I'm seeing both. So, what is kinetic energy? The energy of motion. And so we see that the block is not moving, and so we would fairly say that this has no kinetic energy. But I still think you could argue for the idea that it does have kinetic energy. Does anyone want to argue that? Good. Absolute. Oh my gosh, guys, there's stuff moving around in here at close to the speed of light. There are electrons orbiting the nucleus, sea of electrons inside of a metal, electrons moving back and forth throughout the macro of the substance. These atoms themselves are vibrating very rapidly because these things have a temperature. So now the question is, which one is it? Does it or does it not have kinetic energy? And we are going to say no. And how is it that we are going to say no? Because we get to pick the system, and we are going to say that the system is not the atoms inside the block. The system is the block itself. Does that make sense? Okay, so now we've clearly defined our system, and we are now in the surroundings, and we are all in agreement that that block has no potential energy. Why? It's on the ground. And it has no potential or no kinetic energy. Why? Because it's not moving. So what is its total internal energy? Do you now understand internal energy? The sum of kinetic and potential energy is internal energy. Good? Okay, so guys, the internal energy of this block is 0. Now, what if we want to make it not 0? We want to give this block some energy. Now guys, where does that energy have to come from? The surroundings. That is an important point that makes the Big Bang. I shouldn't say this to you, never mind, you'll get distracted. So guys, that is a very important point, that the only way for energy to go into or out of a system is through interaction with its surroundings. This block cannot make itself move. This block cannot make itself hotter or colder. The only way for the energy of a system to change is by interacting with the surroundings. Now, what are the two avenues through which that interaction can happen? Heat and work, and that's it. Because we are not dumbing this down, because this is college freshman chemistry, and when you become a sophomore in college, they'll really tell you the answer. Guys, those are the only ways energy can get in and out of a system, are heat and work. So, I, as the surroundings, am going to add energy to this block, and I am going to do that through the avenue of work. So if I'm going to do work on this block, what do I need to do to it? Move it against a force. So what is the force that's keeping this block from moving? Gravity, right? Isn't it interesting how that's also the thing that's necessary for potential energy? But I am going to move this block against that force, and as it moves, it now has energy that it did not have down there. Does that make sense? It now has potential energy. So what just happened to the amount of energy that I have? My energy went down. Guess how much my energy went down? The same as this one went up. That's the first law of thermo, and we'll talk about it Wednesday. But guys, the amount of energy that this block gained is equal to the amount of energy that my body lost. And by the way, that amount of energy can be tracked back to my food. But I have now added energy to this block, and this block has energy that it did not have before. Now, what kind of energy, and you understand I'm shaking, pretend I'm not. But guys, what kind of energy does this block have? Kinetic or potential? Potential. Why not kinetic? Because it's not moving, right? Okay, so now let's do this. We're going to lend some funny numbers to this, and I'm going to step down so y'all can see. But guys, the idea then is we're going to say that this block has 100 joules of potential energy. Okay, how did it get 100 joules of potential energy? From me, and so I did 100 joules of work. Okay, so now this block has 100 joules of energy, and it's all potential energy. Now, if this block has got 100 joules of potential, how much kinetic? 0. What's its total internal energy? 100 joules. Now, can we get this potential energy and convert it into kinetic energy? What do we have to do? Let go. And as we let go, what is happening to its amount of potential energy? It's going down. Why is it going down? What's changing? Its position. And where is that potential energy going? Into kinetic energy. And what's happening to the amount of kinetic energy as it falls? It's going up. What part of kinetic energy is 1/2 mv squared? What part of that is increasing as the block falls to give it more energy? The velocity as it accelerates as it falls. So guys, right here it's got how much potential? 100 joules. How much kinetic? 0. As it falls, the potential is being converted to kinetic, but do you want to take a guess what's happening to its total internal energy? It's staying the same, except for air friction. So we are actually losing some energy to heat, because as this falls through the air, it's rubbing against the air molecules and it's warming up the air. But in the absence of any air friction, all of the potential energy is being converted to kinetic energy. 100 joules, right? So now what about this? When this thing is a nanometer above ground, how much potential energy does it now have? Functionally 0, right? How much kinetic energy does it have? 100 joules, and then boom. Now what's its total internal energy? 0. Where did the energy go? Into the surroundings. Some of it went into the table. How? Heat. The table heats up. Did it do work? It made some of the table molecules vibrate. But guys, that is not the major way that this thing loses energy when it hits the table. It's not predominantly through heat. It's predominantly through work. But not work on the table, work on the air molecules around it. And how do we experience that? Sound. Do you get it? So guys, think about everything that we just went through. We went through system. We went through surroundings. We went through work. We went through kinetic and potential energy. We went through the total internal energy changing as that block fell. Then we talked about the idea of recovering energy as this thing returned back to ground. And interestingly, the amount of energy that was lost on impact is equal to the amount of energy I put in. And guys, all of that from a stupid little block of brass. It's crazy. So guys, what are you going to do with this to make sure that you understand everything that you need to understand? Well guys, you're going to take a look. These are all the questions we just talked about. At these ideas. Here are the things that you have got to be sure of. You understand that energy can be converted from one form to the other. What are the two forms of energy? Kinetic and potential. Guys, listen. How does kinetic become potential and potential become kinetic? The answer is not work and heat. It's changing position and changing velocity. Okay? So guys, kinetic and potential can interconvert. Those are internal energies. That doesn't involve work and heat. They can interconvert without interrelating with the surroundings. Then, energy can be transferred back and forth between a system and its surroundings in the form of work and or heat. Does that jive as well? Is there one more? No, that's it. You guys sold on those? Yeah, please. Mm-hmm. Yeah. Mm-hmm.
You caused it to happen.
Right. Exactly.
The block didn't do that.
It can't.
So an outside source did cause that to happen.
Sure, but understand that initially this interconversion, initially this block had no energy. Right. Kinetic couldn't become potential or vice versa because they were both zero. Right. It wasn't until I came along as a surroundingser and gave it energy. Now that it's got energy, that energy can interconvert between kinetic and potential independent of the surroundings. But it got that energy initially from the surroundings. So the amount of energy in a system cannot go up or down without interacting with the surroundings. Once that energy is present, it can interconvert between potential and kinetic without interacting with the surroundings. Is that okay? I'm glad you clarified. So guys, here's your homework. We will grade this on Wednesday, and then guys, we will bring a finer point on this idea of kinetic, potential, system, surroundings, work, and heat. This is why when I moved to the state of Utah, I didn't tell the state of Utah I have a minor in physics. Because when I was in college, I student taught in physics, and I found it hard and exhausting, and I didn't certify in it, so people couldn't force me to teach it. I'd much rather, and you understand why, right? Because any idiot can throw a metal block through the air and think they understand physics. We've never seen atoms, so I can lie to you guys all day and you don't know the difference. So, we'll see you Wednesday, gang.